This is the first video lesson of the equilibrium unit. This is Unit 11. We're going to start talking about what is equilibrium in terms of chemical equilibrium. A good supplemental read would be Chapter 15 in the chemistry textbook. First thing you need to know about chemical equilibrium is that all reactions are reversible on some level, which means given enough time, a reaction that's proceeding in the forward direction will eventually produce enough products that it will be able to start reacting in the reverse reaction. And so I'd like to draw your attention to this little graph in the upper right-hand corner here. This reaction is in dynamic equilibrium, and what you have is an initial reactant of N2O4 decomposing into two NO molecules. Now, before we move on any further, it's important to note that any of these chemical reactions that we're looking at, we're assuming that they are elementary steps. And by assuming that these are elementary steps, what this allows for us to do is to direct the kinetics to be based on the stoichiometry of the problem. And so the rate law for the forward reaction is just N2O first order to the first power, and the reverse reaction is NO2 to the second order or second power. So you can see the rate law for the forward reaction. We call that Kf now for forward. In the last chapter we called it K1, and the reverse would be K -1. But now we're going to use F and R for forward and reverse. So the forward reaction is dependent on this rate law of just N2O4. The reverse reaction is Kr times its concentration of NO2. Now notice that we start with high high N2O4, and it goes down slowly and then eventually levels off. We initially start with zero product, and that's probably what you would expect. Initially we have all reactant, no product. But as the reaction proceeds, you produce more product, and eventually it levels off, and you'll notice that these two are in the middle. Now, what this means is that the forward reaction and the reverse reaction are happening at the same rate. Look at the label of the axis over here. The most common misconception about equilibrium is that the reactions at equilibrium, the reactants and products are at the same concentration. But in fact, it has nothing to do with concentration. It has to do with the rate at which these reactions are happening. In fact, that's such a common misconception that I'm going to go ahead and write that down here in red so that this means business. I will have to remind a handful of you a couple of different times in this chapter that we're not looking at equal concentrations, we're looking at equal rates. And so the reactant and the product are not at equal concentration. In fact, you can see based on the graph alone that we don't lose as much N2O4 as we gain NO2. And at equilibrium, or that point at which their rates kind of meet each other on the same graph, we actually probably have more reactant than product. Now we'll talk about a way to judge which of the two, product or reactant, we have more of at equilibrium using something called the equilibrium constant, but that's coming up here a little bit further down the road. For now, just the concept of equilibrium, and in this graph we're trying to show that their rates are equal at some point. They'll never cross each other, they'll meet and proceed at the same rate until forever, till the reaction stops or until the reaction changes in temperature, and at that point the rates could either go up or down. So let's move up a little bit and clear ourselves out a little bit of room. I'm going to leave the overall reaction there at the top, and I'm going to jot down the two elementary steps in their rate laws. So, like we did in the last chapter when discussing reaction mechanisms, we've got this elementary step that's proceeding both forward and reverse because it's in dynamic equilibrium. And so you can write out the rate laws for each the forward and reverse. But now we're going to talk about, as I mentioned before, F for forward and R for reverse. So here I've combined the two reactants and products rate laws in the forward and reverse, set them equal to each other. Now I want to rearrange this stoichiometrically, not stoichiometrically, but algebraically, so that I get all the constants on one side and all the chemicals on the other. So what I do is I simply use algebra, and I take the Kr and I divide by Kr on both sides, so that brings it over to the left side here, and then I divide by N2O4 on each side, and it brings the N2O4 over to this side. And now if I clean this up and rewrite it, what I have is Kf over Kr is equal to NO2 squared over N2O4. Now this right here is what is known as the equilibrium expression. And this is kind of like a rate law, In fact, it's made from two different rate laws stuck together, but it is kind of the equivalent of the rate law from our kinetics unit. It is an expression of constants and concentrations, and it is a very, very, very important concept or aspect of the equilibrium unit. I'm going to free up a little bit more room underneath here and talk a little bit more about the equilibrium expression. If I combine Kf over Kr and assign it a new constant, in the kinetics chapter we said it becomes a new constant. But now we actually have a name for it. It is known as Keq, or the equilibrium constant. And the equilibrium constant is always set equal to the products of the forward reaction over the reactants of the forward reaction. And so you always express an equilibrium expression as Keq equals products over reactants. Now when it comes to writing out an equilibrium expression, the state of matter matters, but we'll get into that in a little while. But as far as you need to know right now, the equilibrium expression, Keq, which is derived from the K forward over the K reverse of the kinetics constants, is equal to the products of the forward over the reactants of the forward. Now we're going to talk a little bit about the equilibrium constant. Keq is a generic way of expressing the equilibrium constant. But you can express the equilibrium constant in two different ways. You can express it in terms of concentration of aqueous reactants and products, or you can express it in terms of the pressure of gaseous reactants or products. If your reaction happens with aqueous reactants and products, then of course you'd express it as the concentration of products over the concentration of reactants. But this is something that catches students by surprise every once in a while, and this will happen on our test and on the AP test. And if you use concentration when you really need pressure, you're going to get points marked off. And so if you have a gaseous equilibrium situation, you want to use the pressure of the products over the pressure of the reactants. And if you use pressure, you should use parentheses, not brackets, because brackets assume aqueous solutions. So if you use brackets around pressures, you're going to get it wrong. I will tell you that this will happen on our test, and someone will do brackets when they really mean pressure. I'm going to write out the equilibrium expression for this reaction, this very generic reaction, where I've got A moles of A and B moles of B and C moles of C and D moles of D. I will express K as the concentration of C, since it's aqueous, to the C power over the concentration of A to the A power times the concentration of B to the B power. I do not include the D as part of the equilibrium expression because it's a solid, and you can't have a concentration of a solid. Just pick out the aqueous reactants and products and put them into the equilibrium expression, and that is how you handle heterogeneous equilibrium. I suppose I should put in a double arrow here because this reaction is at equilibrium, but we do not include the solid as part of the equilibrium expression. Well, that takes care of this video lesson. We're starting off talking about what chemical equilibrium really is and the equilibrium expression and basics on equilibrium constant. The next video lesson will take you through different aspects of the equilibrium constant, different properties of the constant and what they do and what they mean. So that takes care of this one for now. Thanks for listening.